All right, so my name is Ryan Slaybaugh. I will be narrating this PowerPoint for you. And start off, we decided to do our project on a dynamic queue data structure. And when I'm done with each slide, I will say next slide, so you know to move on. Next slide. Basic overview. A dynamic queue is a data structure that can grow or shrink dynamically. What this means is that as more elements are added to the queue or taken away, it can grow or shrink in size with no limitations on the size. And dynamic queues, well, queues in general follow a first in, first out pattern. What this means is that an element will first be entered into the queue, and any elements that come in behind it will have to wait until that first element is finished doing whatever it was doing in that queue in the first place before they can get their turn. For our project, we decided to tackle 3 problems. The first problem was just a basic drive-through scenario, and I will not be going over that in this PowerPoint just because it was rather basic. The second problem that we tackled was a matchmaking environment that a lot of online games use. And the final problem was to traverse a binary tree using queues, and then we decided to try and retool that to reconstructing the binary tree afterwards, but I'll get to that later in the PowerPoint. Next slide. Online multiplayer matchmaking. In a lot of online video games, developers tend to use queue data structures to ensure that players are entered into games in a timely manner, and they can also use it to ensure that players of equal rank are also pitted against each other. For our purposes, we decided to write a program that simulated this. In this way, we basically would enqueue new players into a corresponding ranking queue. I'm not sure if you'll be able to see as well the image down below, but since we didn't have access to an actual server and number of players to try this out with, we decided to just randomly add new players over time as the program looped through itself. And anytime those players were created, they would be given a rank and a name. And then based on their rank, we would add them to either a bronze queue, silver queue, or gold queue. Those queues would slowly fill up with new players, and once they reached a size of 10, we would say that okay, this queue is large enough for a game to be started. And so once those queues filled up to 10 players, we would initialize a game, and basically just simulate the game playing, just random numbers to determine whether the game was finished or not. Next slide. Matchmaker output. To ensure that the program was running as we intended, using a queue correctly, I decided to set up some logs so that we could check and verify that every time new players were being added, they were being added to the correct queues in the correct order. And then once those queues reached 10 players, we could ensure then that those first 10 players were being removed from the queue and added to a new game. The images down below, if you scrutinize them, you'll be able to tell that first on the left you have a program pass at pass number 4, and you can check to verify that each of the queues has more than 10 players. The next pass, pass 5, you can see that the queues have gotten smaller, and if you count through them, you can tell that the player that was number 11 at the gold queue in pass number 4 is now at position 1 in the queue in pass 5, and that all the first 10 players of that gold queue are now no longer there. And then on the right, we verified that the players were being added to those games, and if you cross-reference that each of those with the gold queues or silver queues or bronze queues based on their rank, you can tell that those players that were removed were indeed added to the correct queues, or to the correct games together. Next slide. Binary tree traversal. Initially, we used a queue to traverse a binary tree. Down below, you can see we have a binary tree with 25 as the root. To the left of that, you can see the queues in the orders that we traversed the tree with. So first you had 25, which was pushed into the queue. And then you pushed both of its children, 20 and 71, and then popped it from the queue. Next, 20 was at the head of the queue, and so we grabbed its in this case, its child, pushed it into the queue, then popped 20. That put 71 as the head of the queue, and so we grabbed 71's children, 35 and 86, and so on and so forth. This essentially came out to be a breadth-first search algorithm, which wasn't that useful. It's already been done before. So instead, we decided to refocus on trying to reconstruct the tree after the initial breadth-first search traversal. Next slide. Intended queue parsing. We intended to use a queue to reconstruct the binary tree after our traversal algorithm, and we were going to use both the logic from the algorithm and the binary tree's characteristics in our reconstruction logic. Down below, we have an example of an array of ints that we use to first construct the binary tree. Then we ran it through our traversal algorithm, and that gave us a queue that you see below that, the after traversal queue. And based on the logic, we know that the first element in the queue is the root. And then from there, we were going to use the characteristics of the binary tree and the logic from our traversal algorithm to parse which elements belonged to which subtrees, either to the left of the root or the right of the root, or left of the left child or left of the right child. And we did some whiteboarding to come up with some ways to make this work, but we didn't have a chance to really get together and hash out the full details. So all I can say is this was the initial part of what we intended to continue with this project, and I know we weren't able to really have much to show, but I wanted to at least put it out there of what we intended to do with this and where we might go with this in the future. Next slide. Afterword. This marks the end of our presentation. I just wanted to thank you all for taking the time to listen and look through it, and I hope that my explanations were decent enough to convey what we did with our project. Queues are prevalent in just pretty much everywhere you look. Down below I have a picture of a doctor's office. You know, they use queues to see patients, though sometimes they also will use priority queues depending on the severity of symptoms. But regardless, especially during the times we're in right now, I hope you all stay safe, and thank you again, and take care.